Let's do an optimization problem. This will be a somewhat gentle introduction, but we'll still get at the heart of some of the problems that arise during these problems. We'll look at a cost revenue example. C of x equals x cubed minus 6x squared plus 15x will be the cost to produce x units of something, and we'll measure in hundreds here. And R of x equals 9x will be the revenue generated from those units. And our goal is to maximize the profit. Let me say as an aside, this revenue function is a bit oversimplified, but this cost function is very realistic. We do often see cubic cost functions. So I called this a gentle introduction. There's no picture we need to draw. The variable is given to us, and profit, the revenue minus the cost, is easily found. 9x minus x cubed plus 6x squared minus 15x or negative x cubed plus 6x squared minus 6x. However, although simple in some ways, this illustrates a recurring problem with optimization. We only really have a fixed method for finding absolute extrema on a closed interval. And what interval is this profit function defined on? Well, it certainly got a lower bound. We can't manufacture fewer than 0 units. But it doesn't seem to have a clear upper bound. From the way the problem is phrased, it seems like we could generate pretty much as many units as we want to. And since we're not on a closed interval, there's no guarantee this function even has an absolute maximum. Never mind a watertight method for finding what that maximum is. Here is where graphs can come into play. Some textbooks seem to be very down on technology, and I agree that it's possible to be over-reliant on it. I mean, you shouldn't have to turn to your cell phone every time you need to take a simple derivative. But I don't want to throw the baby out with the bathwater. I think that graphing technology like Desmos is incredibly useful for problems like this. Here is the profit function. Initially, the profit is negative. You're in the red. But if you manufacture and sell enough units, economies of scale kick in, and your profit starts to go up. Manufacture too many units, and diseconomies of scale kick in, and your profit starts to decrease until if you manufacture too many units, you'll find yourselves back in the red. So we won't use this graph to completely finish off the problem. Gotta do something by hand. But we do observe that there are two critical values. The first one represents a local minimum. The second one represents the maximum that you're looking for. Those critical values, let's find them. Here's P prime, negative 3x squared plus 12x minus 6. The derivative always exists. We don't have any critical values due to non-existence. So we'll set the derivative equal to 0. And I don't have any super elegant way of doing this. We'll just plug this into the quadratic formula. I went ahead and did that off screen. And we know from our graph that the smaller of these is a local minimum, and the larger is the maximum we're looking for. So we should manufacture 341 units to maximize the profit.